Well, where are we? Andrew?
Well,
I mean,
we're just near Flagstaff in northern Arizona, and we're in the San Francisco Peaks volcanic field. And there's something like 1,000 of these volcanoes around here. And the little one behind us here, we call that a cinder cone volcano.
You call that a little one?
Yeah, well, it is. That one's about 900 feet high. You imagine from the base of where you observe to its top, Mount St. Helens is about 8,000 feet high, and it blew the top off when the 1980 eruption. This thing, there would have been cinders, but blown up, hot rock bubbled up, molten material, and it cooled up there in the air and then dropped down and gradually built that cone shape. But here behind us, we can see where at some point it spilled out of the cone and it ran across the ground, and we can see it right into the distance out here.
Just a huge amount of basalt, lava.
Yeah, but it's actually small compared to the lava flows that we see in many places. We see lots of indications of catastrophic geological processes in the past, not just one line of evidence, volcanoes, radioactive decay is another line of evidence.
Andrew, I understand that you and a number of other scientists got together and you focused on this issue for a number of years.
Yes.
What did you find?
Well, it was an 8-year program. There was a group of us, physicists, geologists. We wanted to find out, whether radioactive decay had really occurred. Could we trust these dating methods? And we followed a number of lines of investigation that we divided amongst ourselves, but we interacted.
Well, that is the point that has brought me to you, because Steve was pointing me to the great issue that we have, one of the great issues, and that is the age of the rocks and what the conventional paradigm would tell us about how old these rocks are. And my understanding is that we use the present to determine that age. So we want to talk about that. How do we determine the age of these rocks?
Well, first thing is to recognize that this lava flow is, in a sense, an instant in time. It's an event. And when it's molten, you've got all the different elements that have come out of the volcano are all mixed up. And then as it starts to cool, the different atoms of the different elements combine to make crystals, and the rock starts to crystallize. And once those atoms are locked in, any of those atoms that are radioactive, they now start to accumulate the daughter products, what we call the daughter products, the decay products from those decaying parent atoms. And so this has been used as a clock by geologists to date these lava flows. And so it's important for someone like Steve Austin, who's interested in the sediment layers, how quickly do these sediment layers form? How long did it take between this lava flow here and that lava flow here? Is it millions of years? Let's date this lava flow, let's date this one here. And so these clocks, these radioactive clocks, have been very important. In fact, the age of the Earth was not determined on Earth rocks, it was actually determined on meteorites, with the assumption that the meteorites represent material from asteroids in the solar system that formed at the same time as the Earth out of the sun. And so this whole age question dominates the thinking today, because when you're talking about the history of the Earth, the history of man, putting man in his time setting, we want to understand our roots, our origins. The time question is the thing that's so unfathomable for people. We can experience a volcanic eruption today, and within 10 years, most people have forgotten it. And so when we're going back further in the past, we've got to have ways of exploring. And we weren't there. We weren't there as eyewitnesses. So the scientist is like the forensic scientist who's trying to piece together the puzzle for the judge and jury. Now, of course, the irony is the judge and jury prefer to have the eyewitnesses who were present. But we weren't there to see it. And so the scientist is stuck with what we see in the present and then try and make assumptions to understand what happened in the past.
Well, let's look at this a little more deeply, because the issue of age for most people is a question of being able to look at something. I can look at the difference between a young boy and an old man, and I can tell that there is age there.
That's right.
I can look at a little sapling tree or a big tree, and I can tell there's a difference in age. But now you're talking about something we can't see with the human eye. So what is that?
It's more difficult for a rock because we can look at these lava flows and they're so recent they're on the current land surface. We can go deep into the Grand Canyon not far from here, and the basalt looks exactly the same. And so you just can't see from the appearance of the rock. You have to have some other measure. And this is where this idea of a parent atom decaying to a daughter atom with radioactive decay, if we can measure the rate of decay in the present, and we can measure how much of the parent and daughter we've got in the rock, we can use that as an age calculation. Look, let's try and come down to nitty-gritty with this and understand it a bit more. I like to use the analogy of an hourglass. It's a common one, and it fits what the conventional thinking is. It was an old way of measuring time. You could start by tipping the hourglass clock so all the sand grains were at the top. And within an hour, you could time it independently if you wanted to do an objective measurement. Within an hour, all the sand grains would fall to the bottom. So you knew that if you started with all the sand grains up in the top, you left and you went and did something else. You came back, you want to know how long you've been away. Okay, so you make observations, you make measurements, you see that half the sand is still at the top, half the sand has fallen to the bottom. You know it takes an hour for it all to fall, so half and half, it means you've been out for 30 minutes. And so that's what the geologists are saying. You know, if we know the rate of decay, if we know you only had parent to begin with, then if we measure the daughter now and assume that all that daughter came from parent, it's like that hourglass clock. We should be able to figure out how long ago all the atoms were originally just parents in the rock, and that would go back to the time when the rock formed. When this basalt cooled, it locked in all those parent atoms, and then it was like having all the sand grains at the top. Now we come back years later and we're measuring how many of the daughter atoms are down the bottom in this basalt, and then we're calculating, if we know the rate at which they fall, we can do the calculation.
So the sand on the top represents that material that is radioactive.
Correct.
And it is converting into a daughter element. And that's the sand on the bottom.
Two that we can mention that people are familiar with are uranium decays to lead, and potassium decays to argon. Now, the point is that this rate of decay is so slow when we measure it in the present that it takes millions of years for parent atoms to decay to daughter atoms. And so that's ultimately where the millions of years come from, the fact that the decay rates in the present are slow.
But this seems like an open and shut case then.
Well, it isn't quite like that at all. And we can start with this lava flow here. We know that this was fairly recent. We know that from looking how much it's weathered, how it fits into the terrain. And yet if we take samples of this and we use potassium-argon dating, that's the parent potassium decays to argon, we actually get ages that are way too old. We know that. And in fact, there's been a number of studies done where we've taken historically observed lava flows, say in Hawaii, we've done it at Mount St Helens, I've done it in New Zealand. There's plenty of examples in the conventional literature, in the textbooks even, of recent lava flows that have been dated using the potassium-argon method, and they give ages thousands and even millions of years old. And that's because if you look closely at this rock, you would have noticed it as we walked up here, that there's lots of little gas bubble holes.
Right.
And so the volcano also spews out gases, and amongst those gases is argon. So we actually can demonstrate that it wasn't just potassium atoms that were trapped in the basalt, there was also argon trapped in the basalt. So if we assume that all the argon came from potassium, we're calculating a older age. So in other words, instead of having a lid on the hourglass, there's actually no lid at the top or at the bottom out here in the real world. I mean, how do we know? We weren't here to test these rocks for the time that they've been out here. What about the rainfall that comes here? You break open these rocks and you see fractures and you see leaching. And leaching is going to move these atoms around. So it's not like having a closed system where you've got a lid on it. You could be adding more parent, or you could be taking more daughter out, or you could be adding more daughter. And so if you're assuming that it's been closed and undisturbed, if you're assuming that you only had sand grains at the top to begin with when your rock formed, and that now the ones you measure down the bottom have come from radioactive decay since the rock formed, you're going to get horribly wrong with your ages.
So it'd be like walking back into the room with the hourglass. It really is open on the top,
Correct.
going into an open bin on the bottom, and have little kids running around with shovels and sand.
That's right.
You can't really tell how...
That's right, and it's even worse than that. I mean, we've assumed that these processes are constant, but we know other geological processes haven't been constant with time. You would have probably talked to Steve Austin about this. He'll talk about rock layers being formed by debris flows. And so that's not the norm. That's where you get an enormous acceleration of geologic processes, and what we would imagine under normal circumstances takes tens, hundreds, thousands of years to accumulate. It happens within minutes to an hour. You get this debris flow. So we do know, and like I was saying before, these lava flows are small compared with what we've got in the geologic record. So we've got lots of hints that geological processes haven't been at constant rates through time, and we have other hints that the decay rates may not have been constant. See, we've taken rock samples from a number of places. 4 rock units in the Grand Canyon. We collected lots of samples in the Grand Canyon of each of these rock layers. We've done it in other parts of the world. I've done it in New Zealand. And what we've done is we've submitted the same samples to more than one of these dating methods, because the theory says that if the clocks ticked at the rate that we measure them today, and it's been a closed system, then it wouldn't matter if you use potassium, argon, uranium, lead. They should all give you the same result. It's like having a series of hourglass clocks lined up on the bench.
With just different kind of sand.
Exactly. And so we wanted to test that. And so what we found is on the same samples with more than one method, we were getting ages that were different by hundreds of millions of years, or even a billion years in some instances. For example, one of the lava flows in the Grand Canyon, the potassium argon, gave an age of 516 million years. Rubidium strontium was double that, 1,111 million years. And one of the other methods, samarium gave an age of 1,588 million years, 3 times. So we're not talking about small disparities between the ages. We're seeing huge differences by using different methods.
Well, if there is that kind of a difference between all of these dating methods, then that would seem to confirm the fact that we have an open system here, not
Correct.
a closed one.
And if we have an open system, that means we can't trust it to give us dependable dates for these rocks. And that changes the whole thinking about the history of the Earth, because suddenly now these radioactive clocks are not reliable. We've got evidence that rates were faster in the past. Suddenly, we may not be thinking in terms of millions of years. We may be thinking in terms of a history that is much shorter.
But you were saying that this kind of evidence is in the open literature now.
Yes.
Why is it not making an impact?
Well, I've been asked that when I've spoken in university geology departments. I'll get asked the question, well, if this is in the textbooks, why aren't we taught it? And the answer is because there is a commitment to the millions of years. And so once people get locked into that focus, anything outside their field of view that conflicts with that focus is marginalised. And the reason why the millions of years are important, if we go back in the history of scientific thought, Charles Lyell in England proposed millions of years, and they multiplied the ages for the rocks. And that was the foundation on which Charles Darwin built. In fact, he read Charles Lyell's book and was convinced of the millions of years of geological evolution, so he could say, now, given enough time, what we don't see happening in the present, we might only see small changes in the present. Given millions of years, the small changes can add up to big changes. And so if you want to have a world view or a way of looking at the history that says that we got here by chance, random processes over millions of years, then you've got to have rocks that are millions of years old. Otherwise, you've undermined that whole foundation of that view of Earth history.
So time becomes the critical, if not the critical element, a critical element for the conventional paradigm.
Exactly.
And that time has to be deep time.
Yeah, and this was a Scientific American article, a professor of biology at Harvard University in the mid-50s, when he was talking about the origin of life. He's in fact said, time is the hero of the plot. You know, given enough time, what we think is impossible to happen now, given enough time, the impossible becomes possible and the possible becomes probable. And here we are. Yeah. And so that's the nature of what we're talking about.
So deep time almost becomes a magic wand here. That
Yes.
without that, then there's the stark reality
That's right.
that we're dealing with something
That's right.
other
You wave
than...
wave it over the rocks, you wave it over the fossils, and you start to imagine that what couldn't happen in the present could happen over millions of years.
Well, in light of all of that then, what does an individual who holds to the Genesis paradigm, what do they see when we look at these decay rates and all of that scientific evidence? How is it possible for these dates to look so old?
Well, there is something systematically happening, and we believe that the decay rate was going much faster in the past. It was accelerated. So that, for example, a lava flow down the bottom that was, say, deposited in the first month of the flood year, if we're looking at the flood paradigm, it would go through 11 months of radioactive decay at accelerated rates, whereas the lava flow that was formed at the end of the flood year would only go through a few weeks of accelerated radioactive decay. So it would give you a younger age compared to the one down the bottom.
So it'd be like if you had a bunch of hourglasses that you started at an hour apart. Correct. They would all show different times.
That's right, exactly. And that's what you get. Those that are the first form would have more sand grains fall to the bottom. Those that were later would have fewer sand grains, and you get different ages. So you would still get a relative sense of age, which you do get visually anyhow. The layers at the bottom are relatively older than the ones at the top. But how old? We can't automatically assume that we can determine that by the radioactive ages. We can get a relative sense, but not an absolute sense.
Well, I know you spent a lot of years studying this. Is there evidence of that accelerated decay rate?
Yes, there's a number of other lines of evidence that we discovered. I was looking inside some crystals in granites. What happens in a granite, you get the crystals that contain a little higher level of say, uranium. And when the uranium decays, it's like sending out little bullets, like guns. So, you know, a gun fired at a drywall will leave a hole. It'll damage it. And so that's what happens inside the crystal. The uranium atom, it spits out the decay particle like a little bullet, and it damages the crystal. But it can only go so far before it loses its energy. And so you have this damage around the central area where the uranium was. We call it a radioactive halo. It's where the crystal was damaged. And I was studying a lot of it, hundreds of samples from granites all around the world. I was even looking at other types of rocks to see if we could trace this elsewhere. The interesting thing is that it was like having the difference between a handgun and a rifle. Different atoms will shoot bullets different distances, and they'll shoot them faster or slower. And there is an element called polonium within the decay scheme of uranium that has a very short existence. And this was a clue, the fact that we found these halos that were made of polonium only, came from polonium only, were indication that to separate the polonium from the uranium so you could produce a polonium radiohalo had to mean that the uranium decay was speeded up. Because if it wasn't speeded up, the polonium would be lost before it could nucleate to form its own halo. And so I found that in granites all around the world, hundreds of samples. So that was physical evidence that radioactive decay has occurred. You know, some would argue that just because you measure the chemistry of a rock, you know, you've got uranium and lead in a rock, can you assume that that's all the lead has come from radioactive decay? Could it be to do with the chemistry of the rock? And in part it might be. But here, in this instance, we had physical evidence that uranium had decayed and the radiation had damaged the crystal
because of that halo.
Correct. Now, talking about uranium, another line of evidence we looked at is not only does every uranium atom that decays, it produces one lead atom, but it also produces 8 helium atoms. Now, helium is the second lightest gas. And so it gets trapped in the crystal. But because it's chemically inert, it doesn't connect with any other atoms, these little tiny helium atoms will actually leak out of the crystals. And we were examining a granite from in New Mexico, where they had taken samples down a drill hole, and we got samples of the crystals that contained the uranium, that contained the helium, and we looked at the conventional uranium lead age, the conventional radioactive age or radioisotope age, was 1.5 billion years. But we're also looking at, well, what happened to the helium if there was that much decay of uranium to produce that much lead? There's 8 times as much helium. How much of that is still left in the crystal? How much is it leaked out? And when we did those measurements and we found out how quickly the helium leaks out, we could actually have an independent way of dating those crystals by the rate of helium leakage. And the helium leakage age for those crystals was only about 6,000 years. So leakage is a physical process that we can study in the laboratory. So we've got mathematical equations to describe it. It's very well understood. And so that means that in 6,000 years of real-time leakage, we had 1.5 billion years of radioactive decay. And so that tells you that the decay rate had been sped up. So that was another line of evidence. So we've got these hints. We're still trying to figure out why it would happen. Some have suggested it's to do with changes in the binding forces in the atoms. If you change the binding force slightly, or some other external factor causes changes to the binding of the atom, because a lot of this is happening in the center of an atom, in the nucleus, then you're going to change the decay rates by orders of magnitude. And we've got hints of it too. You may be aware, Del, that there's been some papers every now and again. You know, not everyone is locked into thinking the same. They still report unusual things that they observe in the hope that that might challenge the boundaries of scientific thinking. And there's been papers recently where they've noticed measuring decay rates of atoms. They can actually measure the rate of radioactive decay in the laboratory, and they've done it at different times of the day, at different times of the year, in different parts of the world, and they've noticed slight differences related to the solar cycle and to particularly the sunspot cycle. That may well have been affected by neutrinos coming from the sun. And so these are hints that there may be processes that we aren't aware of that could change these decay rates.